Okay, let's talk about visualizing functions. So she says you've been visualizing functions for a long time, but she wants us to take another look at it. So we have just a normal function, a scalar valued function from R to R. And but she says take note of the fact that actually the graph kind of lives in R2, right? Because we have it looks like this, so it's basically in R2. So we can write a nice definition of the graph. It's the set of all x comma f of x, such that x is in x. Or we can write it's the set of all x comma y, such that x is in x and y equals f of x. So she kind of makes an important statement here. The important fact is that in general, the graph of a scalar valued function of a single variable is a curve, a one-dimensional object. So it is actually one-dimensional, sitting inside two-dimensional space. Okay, so we're gonna amplify that a little bit later. So here we have x, and we have one particular x in the domain x, and we take f and we map it over here. So that's just another picture. So what does this mean about a function from R2 to R? Because in this chapter, we're talking about functions of several variables. So we want to consider functions, for example, the next step up from R to R might be R2 to R. So now suppose we have that, a function of two variables, we make essentially the same definition for the graph. So the graph of f is equal to the set of all x comma f of x, but x is a vector, f of x, the x there is a vector, such that x is in x. So this is very similar to this one. She says, of course, x is a vector, so we could call it x comma y, is a point in R2. Thus, this may also be written as this. So it's the set of all x comma y such, what's this? Sorry. Thus, this may also be written, oh, here it is. Sorry. Thus, this, which is here, may also be written like this, because x is x comma y, so we have x comma y there, comma f of x. So this is emphasizing that this graph from from R2 to R is going to be in 3 space. Now, before we saw that the previous example was in 2 space, but the figure itself was one-dimensional. Now the graph is going to be now the graph of from R2 to R is going to be in 3 space, as we see here, because there's 2 commas there. So you have first variable, second variable, third variable, or we can write it like this. But the curve, so to speak, is actually going to be a surface, which is a 2-dimensional object, even though it's sitting in 3 space. Okay, again, another way to write this, or another way to write this, is this, such that xy is in x and z is the output of that. So she says, hence the graph of a scalar valued function of 2 variables is something that sits in R3. Generally speaking, the graph will be a surface. Okay, so let's take an example and see what happens. So we want to take an example of a function from R2 to R. That means we want the input to be in R2 and the output to be in R. So here's an example where the input comes from R2, and since this is all just a scalar, this output is in R. So the answer is shown here. So we see it's going to be a surface. So what does it mean? So for each point in R2, for each point x in R2, the point in R3 with coordinates, so we put in x, which is x comma y, and then the output is going to be this. So this is going to be some scalar, which is here. So we put in x and y, we get this out. So this is the x, this is the y, this is the z. So we're going to get, this is going to be a point in 3 space. So it might be here. Here's the xy, and the point x comma y comma f of xy is somewhere. It's a 3-dimensional object. And then for every other xy point, we're going to, so for every other xy in this plane, the input space, we're going to get a scalar output up here, and together that's going to give us a point. So we could get a surface. Apparently, this is the surface that we would get for this particular function. So, of course, graphing a function of 2 variables like we just did here is much more difficult than graphing a function of 1 variable. So I think it would be pretty hard to draw that. Of course, one method is to let a computer do the work. Nonetheless, if you want to get a feeling for functions of more than 1 variable, being able to sketch a rough graph by hand is still a valuable skill. The trick to putting together a reasonable graph is to find a way to cut down on the dimensions involved. One way this can be achieved is by drawing certain special curves that lie on the surface. So we want some special curves that lie on this surface. These special curves are called contour curves. And they're the ones that are obtained by intersecting the surface with horizontal planes z equals y. So what does that look like? So here's a kind of picture. So if you took a plane, say this circle here is like in a plane, and hopefully it's a horizontal plane. So if we took a horizontal plane, it's hard to draw this here, but if you had this horizontal plane sitting up here, it's parallel to the xy plane, but it's up here somewhere. It's going to cut the surface somewhere, and in this case it looks like it cuts it in something like a circle. And maybe drop that plane down a little bit, it's going to cut somewhere else. Maybe it's going to cut like here, and maybe that also cuts here, who knows. So that's what they're talking about doing. And those are called contour curves. They're the ones obtained by intersecting the surface with horizontal planes z equals c for different values of c. Some contour curves drawn on the surface of example 10 are shown in the next figure, so we saw that. If we compress all the contour curves onto the xy plane, which means basically, in essence, we look down along the positive z-axis, and we create what we think of as a topographic map. So you've probably seen that when you look at a map that's trying to show you mountains and valleys of the surface that is shown in. So let's take a look at that. So if we were to look down from this direction down, what we would see maybe is something like this. So we would sort of flatten all these curves into the xy plane. This is what we would see. And the point here is that, like, this circle, or whatever this is here, might be this one here. So what does that mean? That means that all of the points here in the xy plane, remember this is the input space, the xy plane. So you have a point here, we have a point here, we have lots of points, this shape. Any of the points on this are all going to be mapped to the same height, to this height here. So this is called a level curve. It means that all the points on here are mapped to the same height. All the points on here are mapped to the same height, and so on. So once again, if we compress all the contour curves onto the xy plane, in essence, if we look down along the positive z-axis, then we create a topographic map of the surface that is shown in here. Okay, these curves in the xy plane are called the level curves of the original function f. The point of the preceding discussion is that we can reverse the process in order to sketch systematically the graph of a function of two variables. So if you have this, maybe you could draw this curve. Personally, I think it would be hard to do, but I guess you could do it. So if you had this, you might be able to replicate this surface. So the idea would be first to construct a topographic map in R2 like this by finding the level curve somehow. Somehow you do that. Then situate these curves in R3 as contour curves at the appropriate heights, and finally complete the graph of the function. Before we give an example, let's restate our terminology with greater precision. Okay, so we have the word level curve and contour curve. So these are level curves, and the 3D stuff was contour curves. So the level curves are in R2, they're in the plane, but the contour curves are in R3, right? So the contour curves are points in R3, like this says here, but the level curves are points in R2. Okay, so keep that in mind. Let f be a function from R2 to R, so that's the original function. So this generates a surface, generally speaking. Be a scalar valued function. So scalar value means that this is the output is R of two variables, means the input is R2. The level curve, so we're talking about the level curve, that's these, at height C of f. So height C, well, this just means that at C, okay, at height C of f is the curve in R2 defined by the equation f of xy equals c. So in other words, f is our function, and we set a specific c, and then find all of the points x comma y, all the points in the plane that get mapped to that c, and those specific points will form the level curve at height c. Now it's not really at height c, right, because it's only in the plane, but we use the phrase at height c, because that's where they came from, by drawing a plane at height c of the original function in three dimensions. Okay, so in mathematical notation, the level curve at height c, again, it's in the xy plane, it's in R2, but it's the set of xy, set of points in R2, such that those points or those inputs are mapped to level c or height c. And then we can talk about the contour curve, which is the curves on the surface. The contour curve at height c of f is the curve in R3 defined by the two equations z equals f of xy and z equals c. So here it's the set of all points x, y, z, that means they're in 3 space, such that f of xy is equal to c, and that's also the z value here. Okay, now we're going to go on now, and here we took a plane which was parallel to the xy plane, so a horizontal plane, but we could take any plane and cut the surface. So we could take any plane, it's going to cut the surface in some way, or maybe it won't, but assuming that it cuts it, we can talk about the set of points where the plane cuts the surface. But actually, we're not just going to take any plane. We're going to talk about specific planes. So we're going to talk about planes parallel to the XZ axis, the XZ plane, and parallel to the ZY plane. So if we have a plane which is parallel to the ZY plane, it might cut out over the x-axis over here, but it's going to be parallel to the YZ plane. It also is going to cut the surface in a set of points. So basically, we're holding x fixed and to get the plane, we're holding x fixed and letting y and z be anything. So that's going to give us a plane parallel to the YZ plane. So we're going to call that the section of the graph of f by the plane x equals c. So it's a sectioning of the graph of f by the plane x equals c, where c is a constant, is the set of points x, y, z. It's in 3 space, where z equals f of x, y. That's the original function. And specifically, though, x equals c. So the section by x equals c is the set of points x, y, z, such that this, we have our surface, but specifically we're also throwing in an extra equation that x equals c. And the same way we can talk about the section of the graph of f by the plane y equals c, like this. So do they show us pictures? Not right away. Okay. Okay, so example 11 is they're going to try and make a drawing. So they're going to construct the level curves and then the contour curves, and then try and figure out what the graph looks like. Okay, so we'll use level curves and contour curves to construct the graph of this. So what does this look like is the question. By definition, the level curves are the points in the plane, so points in R2, such that this equals C, and we can let C equal various values, or we can also write it's a set of x, y, such that x squared plus y squared equals 4 minus C. Thus we see that the level curves for C less than 4, if C is less than 4, then this side is positive, are circles centered at the origin and of radius square root of 4 minus C. The level curve at height c equals 4 is not a curve at all, but just a single point, the origin. Finally, there are no level curves at heights larger than 4, since this equation has no real solutions when c is larger than 4. So here we can talk about level curves at when c equals -5, -1, 0, 1, 3, 4, but not beyond 4. Thus, the family of level curves, the topographic map of the surface z equals this, is shown in figure 213. So these are the level curves, and there's the c equals 4 is just a dot. Okay. Now we can draw the contour curves, I guess. So c equals 4 is the highest one, c equals 3 is below it, and so on. And they're centered at the origin, so I guess they look like this, and they go, well, here's the last one that we drew, which is c equals -5. So up here it says it's a surface that looks like an inverted dish, like this, and is called a paraboloid. To make the picture clearer, we have also sketched in the sections of the surface by the planes x equals 0 and y equals 0. Really? Where's that? I don't quite see that. But anyway, the section by x equals 0 is given analytically as the set of points in R3 such that this is our function, and x equals 0. So that would be, I don't see it here, x equals 0 would be here. So we'd be talking about this plane, but it's not showing. And this one looks like this plane. But anyway, so it would be the set of points 0, comma y, comma z, such that z equals 4 minus y squared, because when you put in x equals 0, you get that. You get this. Okay, and this one as well. And here we see that these sections are parabolas. So this is one of them, I guess. Right, sorry. This is one of them. But I don't, oh, maybe this is the other one. No. Okay. It's easy to see how this surface has obtained its name. Okay, next one is this one. So they go through some similar process, get these level curves. And then I guess they try to draw those, and they get this shape. And this is called a hyperbolic paraboloid. Okay, now we compare the graph. This is example 13. We compare the graphs of the function, the one that we just did, with this one. So that domain of this one is R2 minus the origin. So why is that? Because we're talking about the ln function, the natural log function, and we can't put 0 into there. So we take that out of the domain, and this function h goes from R2 to R because we put in an x and a y, that's in R2, and we get out some other scalar, so that's in R. So they continue. I'm not going to go through this, but you can look at it, and they get this shape. So it's kind of like a log curve, but it's some three-dimensional version. Okay, so she says that we've just been dealing with functions of just two variables, but we can do basically the same thing here for functions from Rn to R. So we say that the graph of such a function f from Rn to R is a subset of Rn plus 1. Remember that R2 to R was a subset of R3. So R2 to R was a subset of R3. So Rn to R is going to be a subset of Rn plus 1, which means we have, in this function, we have to have n plus 1 elements here. So here we have n elements, then we have one more because f is a scalar valued function, so this results in a scalar. So this is correct. So the graph of f equals this set of points in Rn plus 1. Okay, and we can rewrite this, comma this, as this, such that these are in X, are in the domain. And xn plus 1 equals f of x. F of x. So the form of our definition of a graph extends very easily to functions from Rn to R. And we can even talk about level curves. Of course, we can't visualize any of this, but we can just extend generalize our definition of a level curve to functions from Rn to R. So since we use vector notation, she says it's actually the same definition except for the n here. So the level set at height c of such a function is defined by the level set at height c equals the set of all. Remember, this is going to be before it was when we were talking about a three-dimensional object, the level set was in 2 dimensions. So now if we're talking about an object which is in Rn plus 1, then the level set is going to be in R. So the level set at height C is the set of all points in Rn such that f of x, that these points get mapped to a height of C by f. Another way to write it is like this. The set of all these points such that this equals C. And she says again, while the graph of f is a subset of Rn plus 1, a level set of f is a subset of Rn. This makes it possible to get some geometric insight into graphs of functions of 3 variables, even though we cannot actually visualize them. So remember that if we're talking about a function from R3 to R, we can't visualize it anymore. That requires 4 dimensions to visualize it, right? The domain is in 3 dimensions. Then we need one more dimension, which we don't have. So, but anyway, she says this can give us some kind of, talking about the level curves for this might give us some insight into what this thing is. So suppose we have such a function that looks like this. So again, this is a function from R3, there are 3 elements here, to R. Then the graph of f is going to be a 4-dimensional object, which like this, that satisfies something like this, where the w is the output, is the 4th element in the vector, and is a subset called a hypersurface of R4. So the fact that it's a surface kind of looks like the equation of a surface, but we don't know that for sure. But they're referring to it as a type of a surface called a hypersurface. Hypersurface would be the analogy, the extension of the concept of surface to 4 dimensions, which we cannot depict adequately. Nonetheless, we look at the level sets of f. The level sets, I guess, is the level curves, but we're thinking they're sets of points, I guess, in R3. So we have level set at height C equals the set of all, so again, it has to be in R3 now, right? The set of all points x, y, z, such that this equals C. So we can see that this is a plane. So the level sets of this function here, which we can't visualize, the function we can't visualize, but the level sets are in 1 dimension lower, so they're in R3, so we can visualize those. And this is a plane in R3. Thus the level sets form a family of parallel planes. Right, with each C we get another plane, but it's parallel. They're all parallel, and they all have normal vector I, j, k. So those are the level sets or level curves. Oh, I see. That's why they're not calling them level curves, because they're not curves, they're planes. So I'm not quite sure how this helps us to understand the function, but I guess it's better than nothing.